Hello, this video is to help you develop the idea of a motion diagram. Really, this is a super simple diagram that allows you to illustrate motion very quickly and easily with a few dots, arrows, and some symbols. You don't need any more messy drawings of Dawn, Donna, Sandy, or Mikey, and of course Tucker. Speaking of, let's illustrate the last situation in the previous video with motion diagrams so you can guys get some practice. So it's a situation you already know, and we're just going to illustrate it using motion diagrams instead of a sketch, just so you guys can get some information on that and practice. So just to remind you from before, Dawn and Donna were driving east at 15 miles an hour. So let's just represent the motion of the person or people from the perspective of the sidewalk. Let's define east as positive. So what I'm going to do, I'm just going to say west is over this way, and that's going to be negative. And then east, which is going to be on this end, is going to be positive. The reason why you want to use positive and negative instead of west and east is because later on, when we do the maths and stuff, it's a lot easier to associate that with positive and negative numbers. So that's what you definitely want to use. So Dawn and Donna were moving east at 15 miles an hour. So I'm just going to make Dawn and Donna red. We're going to make them red. And so Dawn and Donna are moving east at 15 miles an hour. So I'm going to start with a dot. All motion diagrams start out with a dot. And then as time goes on, I'm going to actually make my line a little bit bigger. There we go. Dot, and then east 15 miles an hour. Very nice. I'm going to make a couple dots. Now notice how the spacing between the dots are pretty much the same, okay? That means that Dawn and Donna are moving eastward at a constant pace, meaning they're not getting faster and they're not getting slower. And we indicate the direction that they're moving in with some arrows. So you can see an arrow there, an arrow here, and the arrows extend, and you see that. Okay, normally since we're fitting multiple diagrams in one, I have these big signs. I'm just going to include these small signs just for the individual diagrams too. Okay, and because it's a constant motion, I'm going to say something very special that you're not going to know about yet, but I'm going to say that their delta V, meaning their change in velocity, meaning if they got faster or slower, is equal to 0, just to label my diagrams just a little bit better. Okay, so this is Dawn and Donna. So Dawn and Donna are done, and now we need to go back to the other end and see Sandy. Now Sandy is kind of a unique case. She's not really moving at all. So if you wanted to represent Sandy using a motion diagram, then the only thing you're going to need to do is make one single dot. And that one single dot that's gonna be it. And then you're gonna have a negative and positive, and of course your delta V is going to be 0. You're going to see that all the diagrams today are going to have a delta V of 0. There will be cases in the future where the delta V, or the change in velocity, is not 0. We'll get to that when we get to that. Okay, so we have Dawn, Donna, this is Sandy. And then, of course, we have Mikey. Mikey's walking in his tracksuit, and he's moving west at 4 miles per hour. Now, Dawn and Donna were moving at 15 miles an hour. So just take a look at those arrows and the length of those arrows. So if Mikey is walking at 4 miles per hour, I would say about a third, a little less than a third of how fast Dawn and Donna are moving. How big do you think his arrows are going to be, or rather the spaces in between the dots? Okay, so Mikey might have something like this. So the dot, and they're really close together because he's not moving very quickly with respect to the sidewalk. That was good enough. And then small arrows like that between his dots. Here's negative, here's positive. His delta V is still equal to 0, and here's Mikey. Mikey. Okay, so that's what we have so far. Don, Donna, Sandy, Mikey, and this is a lot easier to represent using these diagrams than it is with a sloppy picture. Okay, and you can make these up really quickly. One thing that I want to get through to you guys is that these dots represent something very, very specific. Okay, imagine Don and Donna, their car had a oil leak, right? And so these dots would represent the drops of oil on the ground, assuming like each drop of oil was dropped at even time intervals. So let's say the drop of oil dropped every 1 second. You'd see a drop on the ground, and it'd make almost like a motion diagram on the ground. And let's say Mikey was sweating, and his sweat was dripping on the ground, which is kind of gross. But if his sweat was dripping on the ground, then he'd leave a trail of sweat, that would represent his motion with these dots. So that's kind of the idea how you should think about motion diagrams. It's almost like dropping a breadcrumb behind as you move, so that somebody else could go back, look at those breadcrumbs and say, oh, this person was moving in a certain way. Okay. Last but not least, we have Tucker. And Tucker's moving really fast. Tucker's moving 21 miles an hour. So he's moving faster than Don or Donna and much, much faster than Mikey, but he's moving west. So I'm going to give this guy. So he's moving faster than Donna. So that's maybe a little farther apart. There you go. Perfect. And then we have the arrows in between them. And you can see that the arrows show the direction that they're moving in. Going from positive east to negative west. The delta V is still 0 because there's no increase or decrease in their velocity. And you have Tucker here. So that's how you draw motion diagrams for the previous situation that show the motion without using any sloppy pictures. Okay. I'm going to draw another set of motion diagrams for you, and your job is to tell me a story of how each object sees each other move. So the same thing with Don, Donna, Mikey, and Tucker, and Sandy, but now I'm just going to give you diagrams, and you're going to tell me how they see each other move. Okay, so using the idea of relative motion. Also, this time, instead of miles per hour, I'm going to be using meters per second. The reason why I'm using meters per second is because that's the way we measure how quickly things are moving in physics. We don't use miles per hour, we use meters per second. So we're going to be using this type of measurement from this point forward. So I ask you to use that and change that in your papers because we're going to make it a permanent change. Okay. Okay. So let's see. Let me get a new page for you here. All right, sweet. So first thing I'm going to do is I'm going to put down my directions. So I'm going to make this way positive. I'm going to make this way negative. Sure, why not? It's a little different. Okay. And I'm going to say the red object, very technical term, the red object, is going to move in the positive direction at 12 meters per second. So I'm going to make that, looks like 12 meters per second, sure. Okay. And yeah, that first one was a little weird, so I'm just going to fix that real quick for you. That looks better. All right. So it's moving in the positive direction at 12 meters per second. And delta V equals 0. Okay, the 12 meters per second there is just to give you a reference of how quickly it's moving. Okay, the next object is going to be a blue object. And the blue object is going to be moving in the negative direction at 10 meters per second. Okay, so I got to be careful with this. 10 meters per second. So this was about not that far away from each other, so I'm going to make this that far away from each other. So you can see it's moving slightly more slowly overall in the negative direction. So we can 1, 2, 3, 4. We have positive, negative, delta V equals 0, and it's 10 meters per second in the negative direction. Okay, see how I indicated as moving the negative direction of that negative 10. Okay. Also, another tip when you're making these diagrams, you don't need a million dots. You need 5 or 6 dots. That's it. Okay. Don't give me 2. That's not enough. But give me like 5 or 6 dots. That's all you need. You don't need to make like 20 dots in order for me to understand your diagrams. Okay. Then we have a green object. Aha. Moving the positive direction at 9 meters per second. Okay. So green object. Okay, green object moving positive direction. 9 meters. So it's actually going to be really close to the, if like the distances are going to be really close to the blue, maybe a little bit closer. I'm going to see if I can do that. Pretty close to the blue. Sweet. And then we have this guy. Positive direction. And then we have positive 9 meters per second. You might notice I didn't put a positive there on the 12. If you don't see it, it's implied. It's not necessary to imply to show that it's positive. And then finally we have, let's say, the white object, and then that's moving at 1 meter per second in the negative direction. Okay, so this is going to be really tough for me to draw. White object, barely moving. Boop, 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 boop. I'm going to do an extra dot just because it's a really small diagram. Extra 2 dots. Okay, and then this is going to be difficult. A little tiny arrow. Okay, between those dots. Then we have negative, positive, delta V equal to 0, and negative 1 per second. Okay, so now you need to tell me how the red object sees the green, blue, and white objects, how the green object sees the red, blue, and white objects, how the blue object sees the red, green, and white object, and how the white object sees all the other objects move from their perspectives. Okay, put that down in your paper. We'll discuss the answer in class. Thanks very much, guys.